Okay, so in the last video we talked about nuclear power. We talked a lot about nuclear power. Um, Nuclear power compared to, generating electricity through the use of fossil fuels has some key fundamental differences that we talked about. But at the end of the day, you're still basically using a thermal power station. You're still basically, using heat to heat up water, to produce steam, to turn a turbine, to turn a generator that uses electromagnetic induction to create electricity. And where the heat comes from and how to get to work, of course, is different with nuclear power, but it's still similar in a lot of ways to how we generate power using fossil fuels. Now, we're going to move on to renewable energy sources, which tend to be a little bit different than fossil fuels or nuclear power as far as electricity generation goes. And so we're going to start off by talking about wind power. We're also later going to talk about pump storage and solar power. Now, there's not a ton of equations in this unit. There is one having to do with wind power that we're going to derive today, and so do make sure that you pay close attention as we're going through that derivation so that you understand what the equation is, how it works, and why it works the way it does. All right, so let's talk about wind. Um, so of course you probably know this, but naturally occurring wind can be used to generate electricity through wind generators. And basically, we've talked about electromagnetic induction before. Electricity production, for the most part, unless you're talking about like a battery or something, it's created through electromagnetic induction. You somehow get a coil or a loop of wire to rotate through a magnetic field, and that changing magnetic field produces a current. And so in the case of the wind turbine, as the turbine goes around, that spinning motion turns that loop of wire through a magnetic field and produces electricity that way. And you can actually create, wind farms, so to speak, where you not have just one generator, but you actually have like a bunch of generators. And these tend to be located by water because if you're by like the water, you're by the ocean, there's higher wind speeds basically. And as we'll see, wind speed is the key factor in determining how much power can be generated through a wind generator. Okay, but this is kind of what this looks like. Of course, you've got the blades that you can see that spin around, and then at the back you have a box that has like the gearbox, as you can see, and the generator inside, where that wire is spinning through that magnetic field. Okay, and so that's basically how a wind generator looks like. And so basically what happens is as it spins around, it's driven by the wind and it collects the energy um, of the wind, the kinetic energy of the wind that's traveling through its kind of surface area. And so you can see as the turbine spins around, the surface that the wind is traveling through is actually the surface of a circle that you can see. Okay, and so generally speaking, wind power, if you were, this is not a Sankey diagram, but if you were to make a Sankey diagram for wind power, it would kind of start off looking something like this. You've got solar power, heat comes from the sun, and then that creates temperature gradients in different parts of the earth. Some parts of the air have a higher temperature than others, and so that causes, wind. Uh, it causes the air to move, which we call wind, and so the wind has kinetic energy, and the wind, as it goes through the turbine, transfers its kinetic energy to the kinetic energy of the turbine, which through electromagnetic induction is going to produce electricity or electrical energy, as we've talked about. All right, so that's basically the premise. Now, let's say we want to go about calculating how much power can we get from a wind generator. Okay, so we're going to start off with this derivation. Make sure you follow closely along as we go through the steps in this derivation. And we're going to start with the equation for kinetic energy, which we've seen before in the past. 1/2 mv squared, where m is the mass and v is the speed, and ek is the kinetic energy. And so the kinetic energy we're talking about in this case is the kinetic energy of the air going through the spinning turbines. All right, and so in this context, m would be the mass of the air and v would be the wind speed of the air. All right, so notice that it's going through an area of a of a circle, right? And so let's say, hypothetically speaking, let's say the air has a density, which we will give the symbol rho. And so rho is a symbol for density. In this context, we're talking about the density of the air, just like normal density. What that means is that the mass of the air is going to be equal to the density of the air. I'm just going to write a rho. I'm not going to do the subscript air, times the volume of air that we're talking about. All right, stick with me. So this V is not speed, this V is volume. Now notice as the wind goes through the turbine, this is basically what we have here is a cylinder. Okay, and so when we talk about V, the volume of air, we're basically talking about the volume of air of the cylinder. And the volume of a cylinder is pi r squared times h, where h is the height of the cylinder. Right, so the mass of the air at any given point is going to be that air density times pi r squared times h. Okay, but remember that that this air is moving with a velocity v, and so if it's moving with a velocity v, then we also know that d equals v times t, and so we can also say that the height of this air cylinder is basically the velocity of the wind times some amount t. And so in some amount of t seconds, the wind going through at a velocity v travels through a height h. And I guess height's not the best term. I think on the next slide that they use the symbol d, which might make more sense, but whatever. All right, so the point is this. We can actually replace in the equation, we can actually replace the mass with the rho, which is the density of air, times pi r squared. Notice the radius in this case is going to be the length of the blades, right? That's going to be the radius, times, and instead of h, I'm going to put v times t. Okay, so most of that was just for mass, and then in the equation I still have v squared. And so if you simplify this out, you get 1/2 times rho times pi r squared times v cubed, because you have v times v squared, that's v cubed, times t. And we're almost done with the derivation. This expression would allow us to calculate the kinetic energy of the wind going into the generator in some time t, but we don't really want the energy, we want the power, and power, as we know, is energy over time. And so to go from to go from energy to power, I'm going to take the energy and divide by the time. And so if you divide both sides by t, let's say I divide this by t, I divide this by t, on the left side, I have the power supplied by the wind. Okay, remember that this is just taking the kinetic energy of the wind and putting it into the generator. The t here cancels, and I get this equation right here. And this equation, it is given in the data booklet, I believe, but you do need to know what it comes from and to what type of energy it applies. Okay, and so this equation essentially allows you to calculate the power supplied by a wind generator. Now, if you follow the derivation that we just did closely, you need to understand that we're making a big assumption here. Okay, number one, we're assuming that the wind speed didn't change during this process. Number two, we're also assuming that the density of the air did not change during this process, which is not necessarily true. And most importantly, we're assuming, basically, think about where we started in this equation. We were using the equation for kinetic energy, and then we applied it to the wind. So this whole equation came about applying the equation for kinetic energy of the wind. And when the wind hits the turbine, it spins, but it's not necessarily the case that all of the kinetic energy from the wind goes into the turbine, right? In fact, that's definitely not possible because think, if every single ounce of kinetic energy went from the wind into the turbine, that basically means the air is just going to stop moving because it has no more kinetic energy, which is not possible. And so this equation that we just derived, it is limited in the scope in which it's actually correct, and you would be expected to know and be able to talk about the limitations of this equation and why it might not be completely accurate. But with that being said, if you know buy into the assumptions that I just discussed, then this equation allows us to calculate the power generated by a single wind turbine. All right, so pause there, make sure you add that to your notes. Okay, and then the next few slides are basically kind of going through the derivation that we just arrived at. Notice that they actually write A. They don't write the pi r squared out. A would be the cross-sectional area, but of course, if it's spinning in a circle, then of course the area is going to be pi r squared. Again, where r is the radius, and that's basically represented by how long the blades are. Okay, so when they give you the blade length in the problem, that's basically giving you the radius. All right, so let's take a look at some examples. This is basically showing you the data booklet itself. Under topic 8.1, which is where we're at, there's the equation. All right, so we just went through the derivation. That derivation works for the maximum theoretical power from a wind generator. And of course, we talked about why this value cannot realistically be met due to factors like, we're assuming that 100% of the kinetic energy of the wind can be used, but of course, the wind is still going to have some kinetic energy because it's going to keep moving after it goes out the other side of the turbine. It assumes the generator has 100% efficiency. Um, it also just kind of works for one generator where like if you have like 100 generators, if they're close enough together, then the air coming through one affects the air going into the next one. And so the presence of other nearby turbines can also affect the mathematical calculations. Okay, and so there are, of course, assumptions um, made in this derivation. One thing I want to draw to your attention that shows up a lot in IB questions is the fact that of everything in this equation, we basically have three variables. We have A, which is the cross-sectional area that has to do with like the size of the turbine. We have rho, which is the air density, which is not really something we can easily control. But by far the most important factor in this equation is the speed of the air, okay, because it's V cubed. Okay, think about that. We've never seen anything cubed before in an equation. We've seen squared but not cubed. That basically means if we were to double the wind speed, okay, that means if it increases by a factor of 2, 2 to the power of 3 is 8. So if the wind speed doubles, that means the power generated by that turbine is going to increase by a factor of 8. And if the wind speed is tripled, the power would increase by a factor of 27. And so what I'm saying is two things. Number one, you can expect to see proportional reasoning questions related to this equation on your test. That's very common to see. And we've seen those types of questions before. And number two, obviously when you're producing wind generators and you're trying to figure out like where to put them, you have to weigh in the fact that air is such like an overwhelming factor. The airspeed is such like a giant factor as far as how much power you're going to produce. And so I said before that wind speeds tend to be really high near bodies of water. The problem is people also want to live by bodies of water. Like they want to live on the island or they want to live by the beach. And, you know, if you have a beach house, you don't necessarily want like 100 wind turbines like on your beach because that's not really attractive, and also makes a lot of noise. And so um, that's just something to kind of consider. Here in this example, you can just kind of see like a basic calculation, just to give you an idea of what this type of problem might look like. So the question says, since the air is still moving after passing through the rotor area, obviously not all the kinetic energy can be used. The maximum theoretical efficiency of a wind turbine is about 60%, which is higher than the 50% we got for a natural gas power plant, but still, it's limited. Given a turbine having a blade length of 12 meters, a wind speed of 15 meters per second, and an efficiency of 45%, find the power output. And you can see this calculation here. It's just a matter of plugging numbers into the equation. It's not anything super complicated, so I'm not going to like write that out or anything. You can see the calculations here on your own. But notice that this one single turbine produces 410 kilowatts, which is probably enough to power a couple houses, I would think. Probably not a whole city, depending on the size of the city. Um, but 12 meters, that's a lot for like a blade length. Like think about the length of 1 meter. Like the average human is probably like between 1 meter and 2 meter in height. Okay, and so think about having a blade length of 12 meters. Think about having three of those blades and the size and space it would take to accommodate that. Um, and also consider that this one turbine is probably not enough to power a whole city. And so if you want like a significant amount of power, you would need, more than one of these. You'd need a couple dozen or a couple hundred even um, to build like a wind farm. And you can kind of see that there. All right, so here again, I just kind of want to show you this problem is already worked out. And so I'm not going to work it out because you can see the question, you can see the work for yourself. But basically the problem says air of constant density 1.2 kilograms per cubic meter is incident at a speed of 9 meters per second on the blades of a wind turbine. The turbine blades are each of length 7.5 meters, so that would be like the radius. The air passes through the turbine without any change of direction. Immediately after passing through the blades, the speed of the air is 5 meters per second. The density of the air immediately after passing through the blades is 2.2 kilogram per cubic meter, and the turbine and generator have an overall efficiency of 72%. So already they've thrown a lot of stuff into this problem that goes beyond the assumptions we made in our original equation. And so to actually answer this question correctly, we have to do some calculations that you can see down here. This is why it's really important that you understand the derivation and you understand the concepts involved and why the equation is what it is, so that you can understand how to make adjustments if you see a problem that you've never seen before. So for example, you need to understand that the equation that we've been working with, the P equals 1/2 rho A V cubed, essentially comes from kinetic energy. Okay, and so you have the kinetic energy of the wind going into the turbine, and you have the kinetic energy of the wind coming out of the turbine. And the difference is absorbed by the turbine itself. So you've got some energy going in, then the wind comes out the other end. Okay, however much energy the wind lost went to the turbine blades. Okay, that's what I mean by understanding the concepts, because if you understand how to break it down like the way I just did, then you can start to figure out how to do the calculations. And so you see what they did here. They found the power in. So basically, they just use the equation for the power in. They give you, the original density. They give you the speed when it hits the turbines. They calculate what that power is, and then understanding that the power extracted, the power that actually goes to the turbines, is basically the difference between these two powers. They also found the power of the wind on the other side coming out of the turbine using um, the new air density and the new air speed. And so the air slows down after it goes through the turbines. And then they just subtracted these two. Because again, however much energy was lost by the wind's kinetic energy had to go to the turbines, and therefore is what's useful. Right? And so this is how much power is extracted from the air by the turbines. They just subtracted these two and then put it in kilowatts just to make it easier to read. Now, does that mean that's how much electricity is produced? Well, no, because it also tells you in the problem that the turbine and generator have an overall efficiency of 72%, right, which is higher than than really it should be, because really it's probably more like, 50 or 60% actually. And so this calculation only lets you tell like how much of the kinetic energy of the wind went into the turbine, right? That's great, but we don't get all of that out in the form of electricity because of the efficiency thing. So if we want to go the next step, what is P out? Well, that would be 0.72 times 53 kilowatts. And somebody's going to ask me about the units. Do we need to convert to, watts? Can we leave it in kilowatts? I will say in this unit, generally speaking, the IB tends to be okay with you using like megawatts or kilowatts. As long as what you're doing is correct, then it's, pretty fine. Okay, this is 38.6 kilowatts, right? Which is not a lot of power, relatively speaking, when it takes like, hundreds of megawatts to power a city, because then that means you need like hundreds of these things and possibly even more, because if you have them stacked up against each other, that might decrease the overall efficiency even more. And so you start to realize like, wind power has a lot of great advantages because it is a renewable energy source. But there's also disadvantages. They don't produce as much power for the same amount of like investment costs as fossil fuels, because you actually have to build the turbines, right? You have to find a place to put them where they're not going to bother people. Then you have to like maintain them. And then, they make a lot of noise. They take up a lot of space. They annoy people. And plus, it takes a lot of them to actually get enough power to be meaningful. Okay, and that's not to say that wind power is not a good thing. Just just to make sure that you understand that when we talk about energy sources, some people think like renewable and non-renewable is like, good versus bad. It's not that one is good and one is bad. All energy sources have pros and cons, and you have to weigh the pros and cons against each other when you're making policy decisions. All right, so that hopefully gives you an idea of what this type of energy calculation might look like. This is actually kind of more complicated than most problems you see with wind power. Most problems you see with wind power are not quite this involved. All right, but pause there if you need to look at that some more. Okay, so I want to come back to that in just a second. Just to show you some other examples of multiple choice questions that you might see with wind power. This one says a wind generator produces 5 kilowatts of power for a wind speed of 6 meters per second. And then it says the best estimate for the power produced for a wind speed of 12 meters per second is blank. This is a proportional reasoning question. This is the same type of question we've seen going back to IB Physics 1. This is one of those questions where it's like, if this thing like doubles, how does this other thing change? Right? We've done that type of problem many times before. This is just doing it with a different equation. So if we know P equals 1/2, rho times A times V cubed, rho doesn't change and A doesn't change, right? V is going from 6 to 12. So what happens if V becomes 2V? All right, well then you get P prime equals 1/2 times rho times A times 2V cubed, all in parentheses. And you get 1/2 times rho times A times V cubed times 2 squared, which is 8. And so I said this before, if the wind speed doubles, the power produced is actually going to increase by a factor of 8. And so if you take 5 kilowatts and you increase it by a factor of 8, you get 40 kilowatts. Okay, common type of problem to see as far as IB questions go with wind power. They're basic proportional reasoning question. All right. Let's see what else. Okay, so that one we already saw. Um, I do want to talk about a few more examples, but I think we might do those in class as warm-up questions, just to kind of show you, to sum up advantages and disadvantages of wind power. These are just a few that students in the past have come up with. As far as advantages and disadvantages go, obviously it doesn't produce greenhouse gases. It's a renewable energy source. It doesn't really produce any waste on its own, although it can kill birds, which is sad. And it's relatively simple to make compared to nuclear technology. Some disadvantages are it can kill birds who fly into the blades, and we're not just talking about like one or two a year. We're talking about like hundreds or thousands per year, which even if you don't care about birds, it still damages the wind turbine, um, which is then you have to fix the turbine, which is costly as well. It can produce a lot of noise if you have like a bunch of them stacked up next to each other. It doesn't produce as much power as fossil fuel or nuclear power plants. It's unpredictable as an energy source, meaning it's hard to precisely plan like we're going to have this much power available on any given day. In other words, it's great like to supplement existing power sources, but it's difficult to use as like a standalone power just on its own because if the wind speed is like lower one day to the next, then all of a sudden you have like rolling blackouts, and then people are mad because they don't have electricity, and that's not good. All right, so there's advantages and disadvantages to wind power, um, but hopefully everything we talked about in this video made sense. So, as always, please let me know if you have any questions, and I'll see you guys in the next video.